Design of stirrups. Sample problem. The beam shown in the figure was selected using Fy equal to 60,000 psi and Fc prime equal to 3,000 psi, normal weight. Determine the theoretical spacing of number 3 U-shaped stirrups for each of the following shears. So we are given 4 different scenarios here for shear. We have Vu equal to 12,000, B, Vu is 40,000, C is Vu is 60,000, and lastly D, Vu is 150,000 pounds. And this is the shape of the beam. This is a rectangular beam having a width of 14 inches, and the total depth is 27 inches, and the effective depth is 24 inches. So let me just account for the given here. So Fy given, Fc prime given, and this one is implicitly given, meaning to say not really shown in the problem, but this is implied since we are solving for shear. And the strength reduction factor for shear, or phi, is 0.75. We have here lambda. This is a normal weight concrete, so lambda is 1. Beam width is 14, and the total height here is 27, and the D is 24. Diameter of stirrups is 3/8 of an inch, since this one is number 3. The number of legs is 2. This is 2 because this is U-shaped. Okay? So, if we try to illustrate the stirrup here, it has 2 legs. Now, why is the number of legs important? Let me illustrate how the beam behaves in terms of shear. Let's say this is a portion of your beam. Okay, let me just illustrate it here. So let's say you have a shear force here. The beam will have diagonal cracks along the shear, the location of the shear. So to prevent that diagonal cracks, we introduce now stirrups. Okay? That is to help prevent these diagonal cracks, or if the cracks will happen, that is to prevent the further enlargement of the crack. So the number of legs is very important because the strength of the steel reinforcement here is dependent on the area which is running across the crack. Okay, if we draw it in 3D, it will somehow look like this. Let's say you have these stirrups. And if there will be cracks, let's say these cracks, it will be resisted in 2 points, right here and this portion. If I look at this section, the crack will be here at this point, and this will be counteracted by the rebars that you place in 2 areas, here and in this portion. So the number of legs is very important. There are also stirrups that are situated in this manner. Let's say here. So if this is your layout of the stirrups, so it will have 4 legs. But for this problem, this is just a U stirrup, so it has 2 legs. Okay? Now, here, this is 2 legs. And the AV, of course, this is the area of 1 rebar times 2. So the area of 1 is 0.11. Okay? The area of a 3/8 inch rebar is 0.11. Now multiply that by 2 legs, that will be 0.22. Alright? So Those are the given data explicitly and implicitly. Implicitly meaning they are good as given, although not shown in the problem. Okay, so let me now illustrate to you the solution. First is calculate for VU. Okay, now in this problem, VU is already given. For A, this is 12,000. But what if VU is not given? This is how to calculate for your VU. Let me just place it here for convenience. Let's say you have a beam, and this beam is simply supported, and it has a uniformly distributed load. The first thing to do is to calculate for the reactions, and then draw the shear diagram. Okay, so let's say if this one is L and this one is W, your reaction will be WL over 2. WL over 2. Alright? So your shear goes up by a value of the reaction, which is WL over 2. Now, this one is 0 degree because this is a horizontal line with a slope, or without a slope. This is a horizontal line, so this is 0 degree. So the shear diagram will be first degree. And what is a first degree curve? It is a straight line with a slope. So the slope is going downwards since the arrow here is going downwards. So it goes down by the area of this distributed load. And the area of this is simply WL. So it goes down by a value of WL. So this one is WL over 2 less the WL here, the area of the load. So that will be negative WL over 2. And it goes up by the reaction of WL over 2. So this will be 0 here. And this is your shear diagram. And where is VU located here? VU is located D from the face of the support. Okay? So D. And D is your effective depth. Okay? So VU is located here. This is your VU. So since this one is a triangle, you just have to do ratio and proportion in order to solve for the value of VU. Okay? Because this one is L over 2. So we can say that Vmax, let's say here, let's call this one Vmax, or maybe just use the value WL over 2. So WL over 2 is to L over 2, and that will be equal to VU over L over 2 minus D. Okay? Because this one is L over 2 minus D. Alright? So this is how to solve if VU is not given. Now here, for A, VU is 12,000. So let's encode 12,000 here and see what happens. So here, step 2, calculate the shear capacity of concrete phi VC. Okay? Calculate the shear capacity of concrete. But before that, let me just explain to you this formula. Vn is equal to VC plus VS. Meaning to say that the shear capacity of the section, the entire section, is equal to the contribution, both the contribution of concrete, no, this is concrete, and this is steel. Alright? So, the concrete and steel are helping each other to support the entire load. Now, since we are in USD or ultimate strength design, we introduce the factor phi or the strength reduction factor. So, therefore, phi Vn is equal to Vu. Okay? Now, if we try to distribute so that we can solve for the Vs, or maybe manipulate the formula for some other reasons, we can also say that Vu is equal to phi and then Vc plus Vs. And if we distribute, Vu is equal to phi Vc plus phi Vs. Okay? And if we are looking for Vs, we can transpose this here. We can transfer to the other side so that we can say that phi Vs is equal to Vu minus phi Vc. And Vs is simply Vu minus phi Vc over phi. Okay? So, those formulas are important. And for Vc, if we want to solve for Vc, Vc is an empirical formula, no? This is based on research and experiment, and Vc is given by this formula. Vc is 2 times lambda times square root of Fc prime BWD. Hence this blue formula here. Okay? So, calculating, and everything here is given. We are given lambda, we are given Fc prime, beam width, and D. Those are given. Even this strength reduction factor, this is good as given. So, calculating, I'm just trying to locate where each of the values are being referred to. So, you get this 27,605.22 pounds. Next step is to check if stirrups are required. Okay? If Vu is greater than 1/2 of Vc, then stirrups are required. Otherwise, they are not. No, just like in road concreting, wherein the road pavement does not require any reinforcement. But if Vu is very high, such that it exceeds 1/2 of Vc, then stirrups are required. So let us compute for 1/2 phi Vc. And 1/2 phi Vc, using your calculator, or in this case, using my Excel formula, it generated 13,802.61 pounds. And this 13,000 is obviously greater than 12,000. So since this one is greater than 12,000, then stirrups are not required. Okay? And we stop here. This is already the final answer for the question A, which is Vu equal to 12,000. Okay? Now, let's proceed with question B. What if Vu is 40,000? So let us encode here 40,000. If Vu is 40,000, then stirrups will be required because 40,000 is obviously greater than 13,000. Okay? And Vu here, the 40,000 is greater than 1/2 of 5 Vc. Then stirrups are required. By the way, it has here a phi. Okay? So if stirrups are required, let us proceed to the next step. which is to solve for the shear to be carried by the steel. Previously, we have calculated here the shear to be carried by the steel is given by this formula. So this formula here in blue, calculate, and then you will generate this answer. Now, there is actually an upper limit. Okay, there is a maximum quantity of steel that can be inserted in the concrete. And the upper limit is governed by this empirical formula, 8 times square root of Fc prime Bw times D. So here. So obviously, this 16,000 is smaller than 147,000. So therefore, it is within the Vs limit. And since it is within the Vs limit, we can already proceed with step number 5, which is to solve for theoretical spacing of stirrups. Okay? So how do we solve for theoretical spacing? We use this formula. First, let me explain what this formula is all about. Here. From our strength of materials, we know that the shearing stress is the shear force over the shear area. Okay? And if we want to express it in terms of the shear force, we say that the shear force is equal to, transpose it here, so that will be tau times area. And converting it to reinforced concrete notation, this V is Vs, and the shearing stress is Fyt. Okay, Fyt. Okay, let me just put this area one first so that it will be consistent here. So area will be the AV, and the shearing stress will be Fyt, or yield stress of steel in terms of tension. That's why we have here a subscript of Yt. And multiply it by the number of rebars. Okay, area of one stirrup times the number of stirrups. Okay, that's why we have here an N. And N, by this illustration here, N is D over S. Meaning to say the number of bars here is D divided by the spacing. S is the spacing of the stirrups. Okay? Again, the number of stirrups is simply equal to D over the spacing of the stirrups. So plugging in this value here, D over S, plug it in here, we get this. Okay? And then manipulating this formula so we can express the spacing explicitly. So just transfer it here, and then Vs transfer here. So we get this final formula for spacing. Okay? So hence this formula here, AVFYD over Vs. And calculating, everything here is given. We get 19.17 inches. Okay? And that is for the theoretical spacing of stirrups. Next is to compute the maximum spacing as per code. We always refer to the maximum and minimum values as per code. Now, the maximum spacing is governed by 3 equations. Okay, we have 3 equations here. Equation 1, this. Equation 2, this. And equation 3 is the maximum of D over 2 or D over 4 depending on a certain parameter, which is 4 square root of Fc prime BWD. Okay? So, choose the smallest of the 3. And that will be your governing maximum spacing. Okay? So, let's calculate for maximum spacing based on equation 1. AVFYT divided by 0.75 square root of Fc prime times BW. using your calculator, and you can pause this video to solve for this. You will get this value. Next is maximum spacing based on equation 2. AB FYT divided by 50 times BW. And you get this value. Again, use your calculator and pause this video to get this value. Maximum spacing number 3. It's either D over 2 or D over 4. Okay? The choice is D over 2 or D over 4. Now, when can you choose D over 2 or D over 4? Compare it with 4 square root of FC prime BWD. If Vs is less than or equal to 4 times square root of FC prime BWD, use D over 2. If Vs is greater than 4 square root of FC prime BWD, then use D over 4. So let's compute for this value. What is this value? 4 square root of FC prime BWD. So this is the answer. Okay, use your calculator and try to arrive at this answer. So this one, 73,000 is, let's compare it to the Vs. Vs is 16,000. This one is 73,000. So which is greater? This one is greater, the 4 square root of FC prime BWD. So therefore, we use D over 2. Okay? So using D over 2, what is our D? D is given to be 24 inches. So D over 2 is 12 inches. 24 divided by 2. Okay? So comparing the 3, let me check here. We have 3 values for the maximum. What is the governing maximum? The governing maximum is the smallest of these 3 values. And the smallest of these 3 values is obviously the 12 inches. So this is the final maximum spacing. Okay? So therefore, this is already your final answer. Okay? This is already your final answer. Because the theoretical spacing is 19.17 inches and this is greater than the maximum. So therefore, use the maximum. So this is your final answer for number 2 or letter B. Now, let's move on to letter C, where VU is 60,000. If VU is 60,000, let me just encode here, 60,000, then the scenario will be different because the theoretical spacing will be 7.33 and these values here will just be the same, but the theoretical spacing is 7.33. So therefore, the governing spacing will be 7.33. Okay? Because the shear here is getting higher. Now, as the shear force gets higher, the spacing of the stirrups gets closer. And lastly, for D, VU is 150,000. So let's plug in that value here, 150,000. What will happen? At step number 4, the VS is already exceeding the upper limit. Okay, because the upper limit is 147,000 and the VS is 163,000. It exceeds the upper limit. So no need to calculate for the spacing. As you can see here, this one has no value because it already exceeds the upper limit. So for better illustration of all the problems, let me unhide this and give you the answer for all the different scenarios. And you can work this one back using your calculator. Okay? So for A, we have 12,000. If this one is 12,000, then stirrups are not needed. If this is 40,000, stirrups are required. And then calculate all the way down to step number 6. And for C, all the way down to step number 6 also. But the governing spacing is the theoretical spacing, which is 7.33. And lastly, for D, you stop at this step because it already exceeds the limit of your VS. Alright, thank you very much.